what it's like to get burnt by a professor, and I'm not going to do that to you. Okay? All right. Okay, looking at this chapter and the next chapter, chapter 10, elaborates a little bit more into rotational motion. We will actually look at torque, and we will look at angular acceleration in a little more detail. And but this chapter we want to get an introduction, chapter 9, into the rotation of rigid bodies. Oh, and by the way, don't forget, today's lab will not be what's on the schedule. We're not ready for torque. We're going to go back and look at momentum and energy. We're going to look at three types of collisions that can occur: elastic, inelastic, and then neither one. Okay? So we'll be looking at that today in lab. All right? Okay. So, we've looked at linear motion. That's pretty much what our focus has been on all semesters, linear motion. Straight line distance, or it doesn't have to be in one dimension. It can be in two, and it can be in three. You know that. But it follows a straight path, per se. Okay? What about motion through an angle? Now, this is kind of review, but I thought, well, I'm going to go ahead and just put this slide in here just to make sure everybody remembers this. How do we calculate the motion of an object through an arc? Okay? Well, we have to use what is called radians, and you know this from mathematics, from geometry, and from trig, and calculus too, what a radian is. And to complete one revolution or one complete circle, if it is a circle, it doesn't have to be a circle. It can be sinusoidal. It can be a cosine motion. You know that. But motion in general, that's not moving linear, we can measure it in radians. So we complete one revolution, 360 degrees, or as we often say, 2 pi radians. Okay? Now, at the top, they talk about S, which is the arc length, and the radius. Okay, now notice they show us what 1 radian is. When the arc length is equal to the radius, then that's 1 radian. Okay, and of course, you know, if you change your radius, then you change your arc length. You don't move as through much arc here as you do out here. I mean, you know that. If we're close to the point of rotation, or the center of rotation, the axis of rotation, then you know your arc length is not as much as it is out here. So in other words, you're not covering as much distance here as you would out here. I mean, that's commonsensical. Everybody ought to know that just by looking at the diagram. Okay? And that makes sense when you start looking at angular velocity and angular acceleration, how they change with the distance from the axis of rotation. If you've ever watched a wheel spin, like a bicycle, I don't know if you as a kid, if you ever, worked on your bicycle much. I know I was always something like I was working on my bike. I broke a spoke, or a reflector come off, or the tires flat, or whatever. And so we'd turn our bicycles upside down. Sometimes we'd put things in the spokes to make them make a clicking noise, like a straw or something. When you go down the road, you do all that kind of stuff when you're a kid. But if you've ever noticed, when a bicycle tire spins, you can see the spokes close to the center, but you can't see them out at the edge of the rim. Well, why is that the case? Okay, because if you look at its speed, it may have a constant speed, all right, but the motion here is much slower than out here. Well, it's not moving through as much arc here. And the same thing applies to the Earth. When you look at the Earth, because it's a sphere, it's round, well, close, oblate spheroid, it's like an orange. When you look at the rotation of the Earth, you notice here at the equator, everything's a blur, but as you get towards the poles, you can distinguish things a lot better. Notice how the motion here is much slower than it is down here. So the velocity of the Earth, and I'm getting a little ahead, we'll get to that in a minute. The velocity of the Earth at the equator is what, over 1,000 miles an hour. The velocity as you move farther north, and by the way, you can calculate what it is for a given location, given the angle and the arc, the distance from the center of rotation, you can calculate what the velocity is. It's slower as you move towards the poles, and once you get to the poles, what is it? If you stand right on the north or south pole, what's your speed? 0. Yeah. Okay? Why? Because you're not moving through any arc. You're at the point of rotation. Now, when you get into time-light studies, it gets kind of interesting. People that, talk about things in a spiritual nature, and I'm just going to bring this up, just it's not on the test, but, they talk about, well, how can there be such a thing as eternity? Well, if you look at the source of light, or where the light originates from, okay, if you're standing at the source, then would it not appear that everything is constant? In other words, time is irrelevant. Would that not make sense? If you apply that same concept to the rotation of the earth, it makes perfect sense. Okay? So think about it as far as time-light studies. Okay? Light gets really interesting when you really get into a study of light and the speed of thought, too. There's physicists now out there say that the speed of thought is many times faster than the speed of light. We've always said the speed of light's the fastest you can go. Well, there's a lot of debate about that now, okay? But anyway, I thought I'd just throw that in there, and you can go dig it up you can go Google it, okay? And there's some good sources out there, the reliable sources that have some pretty interesting information. All right, so we know that that 360 degrees is 2 pi radians, okay? And so when we find the angle in radians, again, this is old stuff for y'all. You've done this. How do we find it? Well, we divide the arc length by the radius, and that gives us the angle in radians. Now, is a radian a true unit? Yes and no. It's a unit of rotation. So it is a unit per se, but when we start doing some of our calculations, you'll see it will just kind of when we get into angular velocity and angular acceleration, you'll see that there are times when we multiply it, it kind of disappears, doesn't it? You'll see what I'm talking about. It goes away. So in a way, a radian, what is a radian? I mean, let me ask it to you this way. Do you have radian rulers? Have you ever bought a ruler or anything, ever seen a radian ruler?
I've had a
Protractor, but that's in degrees, isn't it?
Well, mine also
Measures radians. Okay, so you can measure it in radians, but typically what do we measure in? We measure in degrees, don't we? So, I mean, I'm not trying to be contradictory here. It has its place, but typically when we take measurements in real life, it's either in what? It's either in meters, inches, feet, or it's in what? Degrees, isn't it? Okay?
A degree. The value, in my opinion, of the radian is because it's based on measurable quantity.
Yes,
Whereas
yes.
the degree is, okay, we're cutting a circle.
Part of a circle, yes. And you're exactly right. That's exactly right, okay? All right. So, how do we find arc length? And how do we find an angle? There it is. And again, you should know this from all the math you've already had, okay? So now let's get into angular velocity and angular acceleration. So when we look at the movement through an arc, okay, now again, we're not talking linear here, okay? We're talking about movement through an arc. And notice how we're moving counterclockwise, okay? We'll get to that why in a minute and why it's important to recognize it as either counterclockwise or clockwise. So to find the average, notice this now, the average angular, and that omega, lowercase omega, represents angular velocity. So please label these units. Now I don't know why in this chapter they did not annotate all of the symbols, so I'm going to annotate them as I go. All right. So average angular velocity is omega. Notice it's the change in arc, which is in radians, through a given time interval. Gee, that really looks very similar to this equation, doesn't it? Right? That looks very similar, and if you want to put a bar above it, typically when we say average velocity, we put a line above it, or we write average, AV. Okay? Either way, same thing. All right? That looks really similar to that equation, doesn't it? Well, they are related. Okay? One's linear, one's in an arc, through an arc, okay? All right, and of course, how do we find delta theta? Well, just like we did delta x, y'all, final minus initial. So that hasn't changed, okay? And please understand that this is the change in arc, or the change, I'll say arc, or the change in the angle, arc. It's better to say arc. Okay. Okay. So if we want to find average angular velocity, we just divide the change in arc by the time interval, and that gives us average angular velocity. Now, what if we wanted to find instantaneous? What will we do? Take the derivative. Okay? You know, anytime I say instantaneous, we got to do what? Take the derivative with respect to time. And we'll get to that in a second. All right, now, this is very, very important. There's another one of these conceptual things that we got to remember. We choose theta to increase in the clockwise rotation. So if theta is changing in the counterclockwise direction, then we say it is positive. Okay? If it is changing, or if it's decreasing, if the rotation is moving in the clockwise direction, then we say it is negative. Okay? Please write this down. Please get this. This is very important. Because when we get to acceleration, you'll see that it really matters. Was it moving clockwise? Was it moving counterclockwise? And which way was your acceleration? How do I know if it's decreasing or increasing by looking at angular acceleration? Okay? So you need to remember that. So counterclockwise. And y'all, if you remember when we measured our angles, how do we always measure angles? I've told you from the very beginning, first week, always, or second week, always measure counterclockwise from the positive x-axis. Okay? And here's one of the reasons why. Okay? Not just so the trig works out, but also when we get into angular motion. All right? Okay. Any question? Okay. So it's negative when it's clockwise, and it's positive when it's counterclockwise. All right? And if you think about it, that makes sense. It makes perfect sense because, look, your angle is increasing this way. Remember, we always orient to the positive x, if at all possible. So it makes sense it's increasing this way. This way it's decreasing. Clockwise it's decreasing. It makes sense. Okay? So it should be negative. Okay? So as I said a minute ago, instantaneous angular velocity. I really don't even need to show you this slide because you should know by now that anytime we're looking at instantaneous angular, whether it's velocity, angular acceleration, linear acceleration, if it's instantaneous, if it's work, whatever, it's going to be the derivative. Okay, as the limit approaches zero or a particular time interval. You should know that by now. That is not changing. It's not ever going to change. Okay? Okay. So we take the derivative of theta with respect to the time. Okay? All right. Very simple. Let's see, what page are we on? Yeah, page 277, okay? So if I want to know the instantaneous angular velocity, I've got to have a function, take the derivative, boom, I get it. And by the way, what are the units here going to be? I didn't talk about that. Very good. It has to be radians, it may say that on here or on a previous slide, per second. Please make sure you get the units. It's radians per second. Okay, radians per second. All right? All right. Okay, any questions? Now, I thought, well, I'm going to go ahead and leave this slide in. Now, if we take an object that's moving, it's rotating, we can use something called the right-hand rule, and we'll use this rule too when we get into magnetism too. Very, very useful. All right. Now, another thing too I almost overlooked. Notice too that it is a vector quantity. Okay? You've got what? You have changing position through a given time interval. You've got what? You've got magnitude, you've got a value, and you've got direction. The arc is the direction. So it has to be a vector quantity. So if I curl my hands around the axle and my fingertips represent the motion counterclockwise, then guess what? My angular velocity is what? It's perpendicular to that wheel, isn't it? It's positive. We say it's positive. If it's counterclockwise, notice my fingers curl in the direction of the rotation, then notice what happens. It's pointing down. And we call that negative angular velocity. Okay? So when we look at our vector quantities and we look at the direction, that's how we do it. We use the right-hand rule. Okay? And curl our fingers in the direction of the motion. All right? Very simple to remember. We'll come back to that next semester. Okay. All right. So just to reinforce what we said, if it's up, it's positive. And notice we use the X, Y, Z here. If it's up, it's positive. If it's down, it's negative. Okay? Notice that it's less than 0. All right? Okay? So again, that's those conceptual things you gotta remember. All right? Rotating counterclockwise, you should have positive angular velocity. If it's rotating clockwise, then it's negative. All right? And again, this is just to show us how we find, angular acceleration. Now, angular acceleration is what? The change in angular velocity. Gee, that looks just like this equation, doesn't it? All right? It's the exact same equation. The only thing we do is change V to omega. It's the only thing we did. All right? Now, what are the units for this? Well, the units are going to be what? Well, it has to be what? Rads per second squared. Instead of meters per second, it's radians per second squared. Okay? So for average, and please note that's average, there's your equation right there. Okay? Or the other one, just use the delta. All right? Now here again, if I wanted to find the instantaneous acceleration, I'd take the derivative, wouldn't I? Derivative of omega with respect to time, right? Okay. And that's what they're showing you right there. Okay? All right. So really this is not any different than, the only thing that's changing, the symbols are changing and the type of motion. But the principle's still the same. Okay? The principle's still the same. All right. Even though it's not linear, to find the speed is still the change in the arc length divided by the time to change, to find the acceleration, the change in angular velocity divided by the time. Still same principle, just a little different application, okay? Now notice this, and I wanted to keep this slide in here. I was just mentioning this a minute ago. Why is it important I know how to determine my angular velocity? Well, if I tell you in a problem that the object has a angular velocity and it's rotating counterclockwise, then you know it's positive. Well, if my acceleration is positive, then guess what we're doing? Speeding up, just like linear motion, right? If you have a positive linear velocity and you have a positive acceleration, you're mashing the accelerator, then you're speeding up, okay? Well, same thing applies if we are applying the brake. Okay, what happens to the angular velocity of a wheel as it's rotating when you start to apply the brake? It slows down, doesn't it? It decreases. Well, the angular acceleration then becomes what? Negative, doesn't it? All right. So remember, you can have positive angular velocity and negative angular acceleration just like in linear, but you got to realize that you're slowing down. Okay. All right. So what is this telling us? If the signs are the same, come on. Holy smoke. This pen just don't want to write today, like it most times. All right, if the signs are the same, we're speeding up. Signs are different or opposite, slowing down. Okay. All right. Same, speeding up, opposite, slowing down. All right. Okay, now, well, hopefully you still have those on your cheat sheet. And notice the relationship here. Final velocity, initial velocity plus AT. Well, guess what? The final angular velocity, the initial angular velocity plus the average, and by the way, that right there is angular acceleration. Okay? And that's alpha, Greek letter alpha. So notice that really nothing changes. The only thing that changes is the symbol and the type of motion from linear to angular. That's the only difference. Notice they're calculated exactly the same way. Okay? Exactly. All right? Now the key there is constant angular acceleration. All right? Constant angular acceleration. Meaning what? That the velocity is doing what? The velocity is changing, right? It's either increasing or decreasing. Okay? All right? Okay. So please, if you want to, you can write those down. We call these our what? Our angular kinematics. Angular motion kinematics, or rotational motion kinematics. Okay? By the way, if you want to double check these, and they do go through each one, and there's no sense in going through each one, pages 278, 279. These are on page 279, okay? Is that right? Yeah, 279. Okay? All right. They're table 9.1. Yeah. Okay? All right, so if you want to go back and look at the relationship. Okay. And of course this is using what? That right there is using the average angular. Don't forget, y'all, that right there is average angular velocity. Okay? It's 1/2. So I could take the 1/2 out and say average. Okay. Just say average angular velocity. Okay. All right. All right, any questions? Okay, so let's continue, and now let's look at the relationship of linear motion to angular motion. Okay, so how can I find, in other words, if I want to know the linear velocity of point P at that point, you got to understand something. It's at that point only, all right? All right. Now, could it be constant? It could. All right. If the speed is constant, we still have centripetal. I'm getting a little ahead of myself. We still have centripetal acceleration, radial acceleration, even with constant speed. And the reason being why is because what's changing? Direction. Yeah. Okay. Yeah.
There's still acceleration even if it's constant speed.
That's exactly right. Yeah. Because remember, always remember, velocity, whether it's angular or linear, is a vector quantity, and you've got to have direction and you've got to have magnitude. Okay? Now, just because one is constant, speed is constant, like he said, if direction's changing, it's still accelerating. And that kind of messes with us. I understand that. But if you'll think about it, it still makes sense, because velocity is not only dependent on the value of the velocity, the magnitude, it's also dependent on its direction. Okay. So we can find, so you need to write that equation down. This is what? This is linear, this is the velocity, this is the linear speed. So linear speed. Right there. So the radius, r, now do I need to tell you r's radius? Come on now, you ought to know by now, r's radius. The radius is from here to here, right there. This is from the origin to the point, okay? And that right there is what? That's angular velocity, isn't it? All right, now, here's what I want to look at, right? Okay? Please don't let me forget to annotate, because there's parts like you've already seen not annotated. All right. All right, now look. All right, look at our units. We've got meters times what? Radians per second. Right?
There's a per second on the other side. Or are we just talking about for the right side?
All right, let me do this.
There we go.
Thank you for mentioning that. Make it a little more clear. So it becomes what? Right? Because we're talking about linear. So the radians kind of cancel out, don't they? You follow me? You don't say meter radians per second. No, because linear is not measured per se in radians, is it? Well, what's 0 degree? Okay. What's 1/8? I understand. Yeah, you could argue that. Okay. Because pi is what? 180, isn't it? Well, that's going straight backwards, isn't it? Okay, I understand you could probably argue that, but still, we're just talking about the linear motion, positive, moving forward. Notice we use the word speed there. So what are we looking at only? Magnitude, right? Magnitude. Okay?
Direction's constantly changing.
Yeah. Because when you get here, the direction's changed. If you're here, it's different than it is there. It's constantly changing. Okay? All right. Okay? So please don't think because we're talking linear, well, that radian still comes in there. No. It kind of cancels out. It's meters per second. Okay? Because it's linear speed. Please get that. All right? It does matter. All right? But what about looking at acceleration? Okay? Now, y'all, we've already talked about, look, this right here should not throw us. Okay? And there's a typo error. I knew there was a typo in there. That should be squared. There we go. Now look. Watch.
Radial acceleration is just r omega.
No, omega squared r. You got to get meters per second squared.
Okay.
It has to be. Yeah, it has to be. Because the radians cancel out.
I'm thinking of
Yeah.
tangential velocity.
Yeah. Okay? All right, so look, now I'm going to come back to tangential in a minute. So look at radial acceleration. Does that equation, whoops, excuse me, does this equation look familiar? Should. We can also define that as what? Oh, my Lord, is it 4 pi? 4 pi squared over r? Or no. It was 4 pi squared r over t. Remember that equation back in linear? 4 pi squared r over t. T squared, yeah, thank you, yeah. 4 pi squared r over t squared. Remember that equation? That's another way to find radial acceleration. Okay. Remember? So don't forget that you could substitute that in right there. All right, and the equation would be a little different, but still it's going to come out the same. I mean, it's going to come out like what I just said it would. Or we can take what? Now remember, there's a typo error here. That should be squared. If you look on page 281, you'll see it correctly shown. You know, you'd think, yeah, there it is. Thank you. Yeah, overlooked it there. All right, now, so we've got centripetal or radial acceleration, and that's what? Center seeking, right? Correct? Towards the center, right? Why does the water stay in the bucket when you spin it on a rope? Well, you've got centripetal acceleration and you've got inertia, don't you? Right? But if you stop the bucket, we know it'll pour out if it's over your head. All right? But that's impossible to do in this dimension. Right? We can slow it down, but it should still stay in there, right? Because of centripetal acceleration and inertia. So that's center seeking. But what about tangential? Again, tangential acceleration. Now notice the little difference here. We've got what? That is what? Radial acceleration, right? Radial acceleration. That's alpha. That's not A, that's alpha. If you can't distinguish it there, you should be able to with this new projector. Right? So the radius times radial acceleration, which is what? Radians per second squared, so we get meters per second squared, right? So, and I'm saying all this, all that to say this, the units here again are going to be what? What are my units going to be? All right. The units for both not changed. The units are meters per second squared. All right. Now let me ask you something. Can I have constant velocity, we've already mentioned this, and have radial or centripetal, same difference, acceleration? Yes. But what about tangential? What happens to the angular velocity with tangential? All right.
It changes in the same direction as velocity.
Okay. So would velocity be constant here if I have tangential acceleration, or would it be increasing at each point? At each point. Okay. So you see the difference. Radial, and it can be changing too with radial, but still we're going to look at it more as what? Tangential acceleration. In other words, this would be with a situation right here where, well, why would we want to consider tangential acceleration? Well, what if the velocity is not constant? What if it's speeding up and slowing down, and speeding up and slowing down, speeding up and slowing down? You see what I'm saying? Your tangential acceleration is going to be different, isn't it? It's going to be different. In other words, radial acceleration would not be constant. If it's speeding up, slowing down, speeding up, slowing down, speeding up, slowing down. You see what I'm saying? So you think, well, these are the same thing. Not really. Because if it's speeding up and slowing down, if the velocity is changing, then guess what? Your centripetal is not going to be constant. Okay? Okay. All right. So units are the same, meters per second squared, but tangential, again, y'all, and it tells you this right here. It tells you this. And that's why I like these slides, because they just kind of condense it into a little, just try to make it simple, into the point. Means that what? It's speeding up. In other words, it has the body has angular acceleration. It's speeding up when we look at tangential. Okay? Here we could have just plain old constant acceleration. Okay? Constant speed, excuse me, but have centripetal acceleration. In other words, it could just be moving at constant speed. All right? But here, with tangential, it's speeding up, or it could be slowing down. It could be doing the other too. It could be slowing down. All right? Please note the difference. Okay? Okay. Units are the same, meters per second squared. All right? Okay. Yeah, and they put it right over here. I don't know why they goofed there. I should have caught that earlier and changed it, but anyway. Okay? Now notice here, why do we use radians and not degrees? Okay? Well, because when we start relating linear to angular, we have to use it. Okay? We don't say 60R. We say what? Pi over 3 radians. Right here. If I want to find the arc length, this is the correct way to write it, not that way. All right. So use radians. Now, does that mean I have to put my calculator in radian mode? No. When do I need to put it in radian mode?
When you're doing trig functions.
When I'm doing trig, that's right. So please don't freak out and put your calculator in radians. You don't have to. You don't need to. You just put pi over 3, put it in, bam, and go, okay? Only when you use trig functions. And we will do some of that next semester, okay? Now, all right, we're talking about motion, so guess what we're also going to get to throw in here? Energy. Because you know as well as I do, if an object's spinning, you ever stuck your finger in the fan? When you was a kid? Yeah. Well, did it hurt? Well, sure it hurt. Well, why did it hurt? Well, because it was spinning. Well, yeah. But because it had energy. You ever run into the door at night? Yeah. Did it hurt? Yeah. The lights are not on? Why? Because your body had energy because it's moving. So it doesn't matter, y'all. If it's linear, angular, it doesn't matter. It's still going to have energy. Think about a saw blade. How does a saw work? I mean, come on. You can't physically take that saw blade and turn it with your hand and do much cutting, can you? Now I know a hand saw, but you have to really, and it's slow, isn't it? Think about a skill saw though. Man, you hit that button and it's moving at what? 5,000 RPMs maybe? It's up there, isn't it? It's really, maybe 10,000. It's really spinning fast, isn't it? And you can zip through it. If it's a good sharp blade, you can zip through a piece of plywood, a 2x12, whatever, just like that, can't you? Provided you got a high amperage saw. Now, if you got one of these little tissy ones, it'll probably, it'll bog down on you. Yeah.
At the end of the day, though, all you're doing is hitting wood metal over and over.
That's what you're doing, but at a high rate of speed, right? Yeah. Mm-hmm. And so, said all that to say this, it has rotational energy, okay? Now here is, and I don't know why they put these equations backwards, moment of inertia. Well, how do we find moment of inertia? Well, right here, okay, right there. Now, what are my units going to be with kinetic energy? Now, come on. Energy's joules, period. Well, how do you get that from I omega squared? Okay. Look, the units for I is what? Kilogram meters squared, right? Look right here. The mass in kilograms times the radius squared, and notice they use the sum of, so it can be, you add these up, okay? It can be several bodies acting together. Well, how do I find the moment of inertia? Then you use I. Now, let me say this. The moment of inertia is different. The way we calculate it is a little bit different based on the type of body. And I'm going to get to that in a second. But this is for what? This is just given for a simple body, just at the center of rotation, okay? This is how we find it. The sum of what? The mass times the radius squared. The units are kilogram meter per second squared. All right, what is omega squared? Well, that's what? Well, we could say radian squared, and technically it would be radian squared per what? But remember, what happens to radians? It kind of cancels out, doesn't it? And I'm using that a little loosely. All right, radian squared per what? Second squared. Okay, y'all, what is a kilogram meter squared per second squared? It is a joule. You ought to know that by now. Okay? So it's there. You got to just look for it. You got to remember your units. For the love of God, when you go to grad school, please don't forget your units. Grad school. Engineering school. Well, it is like grad school. Probably. All right. Okay? I don't know. I think grad school was a little easier, but a lot of work. But anyway. Oh, shoot. Why do I always hit that? All right. I'm getting in a hurry. Okay? Any questions? So we find moment of inertia of a body, kilograms meter per second squared. Now, notice these perpendicular distances of the particles from the axis of rotation. Okay? In other words, it's at a right angle to the rotation. All right, but what about looking at moment of inertia? All right. Have you ever noticed that if you're spinning an object, have you ever noticed how easy it is to spin a top? It's not very hard, is it? Why? Because the mass is pretty much centered. It's close to the center of rotation, isn't it? All right. Have you ever tried to twirl a baton? Now, I know you guys are thinking, well, what the heck would I be twirling a baton? Oh, you know, okay. Spinning a stick. A broom. You always grip it where? Do you grip it on the end or grip it in the center? Somewhat in the center, yeah. Well, what if you add something to the ends of that broom? What if, let's say, you tape a can of spray paint on each end? Let's say we cut the straw off. Let's cut the straw off and put a can of spray paint taped to each end. Is it easy to spin or a little bit harder? It's harder, isn't it? What if I move those cans of spray paint close to my hands? It'd be pretty easy, wouldn't it? Okay? So what am I trying to get you to realize here? That radius between the masses and the point of rotation makes a big difference in mechanical terms. All right? Think about a motor and how a motor spins. If all the weight of the motor was out on the around the perimeter, if all the windings of the wire was way away from the axis, do you realize how many amps it'd take to move that thing, to get it started? Just a simple motor, it would take a horrific amount of amps to get it to moving. But if you've ever noticed the windings of a motor, now it does spread out from, and we'll get into that why later, next semester, but if you ever noticed the windings of the motor, it starts right at the axis pretty much, doesn't it? Pretty close, doesn't it? Electric motor, an electric motor. I'm sorry, an electric motor, yeah. Yeah, an electric motor. You don't have all the windings way out here away from the axis. You start close to the center and then you work your way out. And then you have to get into what's called, three-phase motors. And that's something, because when you get into high amperage motors, most of them are three-phase or maybe even more than that, four-phase. Did you have Glenn Bruce?
Yeah. All we really did was three-phase. We never really talked about
anything beyond that.
Yeah.
But there's a reason for the phases, because if it didn't have the three phases, you'd never get these big motors started because of the torque, because there's so much weight. There's a lot of weight in that motor, in the windings, to get it started, a big motor, to get it started to turning. So it does it in phases. It gets it started, and I think it turns so many degrees, and then the next phase kicks in, and it turns next phase, yeah.
And it's three.
Yeah.
So it keeps it in constant.
Keeps it in constant motion, yeah. Instead of putting all it in at one time, it does it in phases, okay? Well, why? Well, because of this principle here. Not all the mass is right at the axis of rotation. When they get these big motors, that windings are huge. Some of these motors, electric motors, are huge, okay? Huge, all right? And it would take a horrific amount of amps if they didn't do it in phases, okay? Which is more money you'd have to pay the electric company, okay? So likewise, what I just said, if you put it out there, it's a whole lot harder to turn, isn't it? Okay? It's a whole lot harder to turn, all right? But you have a high moment of inertia. So I'm not saying there's not an application for it, For example, have you ever seen these, gone to see these shows they have on is it Discovery Channel, and they show how it's made? You ever watched that? I was watching, I think it was How It's Made or a similar show, and they were talking about car crushers and metal shredders. And they'll take some of these junkyards, they have these machines, they'll put a whole car in it, and it spins like a 300-pound hammer. Well, you know, the hammer's way out here on the end, and it's the point of rotation's back here. And I forget how long they said the arm of the radius or the axis of the arm of the hammer was, but it had like a 200 or 300-pound hammer on the end, and it spun at like 5,000. It was a crazy number, RPMs. Okay? Can you imagine how long it'd take it to get it to going that fast? Here again, you'd need a very big motor. It'd take a lot of amps, but man, once you get it spinning, its momentum will kind of help carry itself, won't it? And they showed it, and it just beat a car to little pieces about, big as a quarter, $50. Just brrr, and it made a horrific noise. I mean, and in like a minute, it was just beat all to pieces, little bitty pieces. So that's an application right there. These junkyards, when they shred these cars up, and it did it pretty quick. And then they put another one in, boom, put another one in, boom. And it does it real quick, okay? All right. So you can process scrap metal pretty fast that way. Cars, anyway. And then sometimes they just crush them. All right, so how do we then determine the moments of inertia of a particular body? Now, this is on page, where's it at? Yeah, page 286. I really want you can add these to your formula card. You can make a separate formula card if you want to. I don't care. But you need these moments of inertia. Now, notice it's extreme, and it wouldn't hurt probably to draw them, just to make a simple drawing. Notice it does depend on where the axis of rotation is at. So if you have a slender rod with the axis through the center, it's 1/12 the mass, that is the mass of the rod, times the length, not the radius, the length of the rod. Okay, that is the length of the rod. What if I spin it at the end of the rod, like I was talking about with the hammer in the car shredder? Well, that would be, you would use this would be one of the equations you'd use, okay, to find the moment of inertia. And when you look at, too, it's kilograms meters squared. Kilograms meters squared. Okay. Think about how much mass is being applied per meter squared of area. Because meter squared is area, isn't it? So you say, well, how do I put that into sensible terms? Just think about it this way. It's how much mass is applied to a square meter. Think about it that way. Of area. Okay?
So really pressure.
In a sense, yeah. It could be. Okay? All right. Well, it's similar, but it's not exact because remember, it's not force, yeah. It's just mass, yeah. And that's why we give it moment of inertia instead of pressure, because force is not involved. Okay. All right. Now, notice it changes. Again, rectangular plane. Notice, wow, look at this. 1/12 the total mass times a squared plus b squared. A, and of course, the width and the length. That is, again, through the center. What about along the edge? It's 1/3. 1/3 m times a squared. Okay? And notice they picked A and not B. That's exactly right. It's perpendicular to the axis. I was hoping you'd see that. Okay? All right. And then what about for cylinders? A hollow cylinder, a solid cylinder, a little simpler equation, but probably the simplest of all the equations is the mr squared. A thin-walled hollow cylinder, excuse me. Yeah. Tire would be that equation. How much moment of inertia does a tire have? Well, you know, good and stinking well, truck tires are going to have a whole lot more moment of inertia. Now I'm talking a semi. I'm not talking about a pickup. I'm talking about a semi-truck, 18-wheeler. Even if it's, you know, well, and two, if you'll look at the kinetic energy, rotational kinetic energy, you know, a moving truck tire can kill somebody. Well, a car tire can too, but even a moving truck tire at a much slower speed can kill someone if it hits them, and it has happened. I had a guy I worked with one time, someone from where he lived, an old man was out in his garden working and lived close to the highway, and a wheel come off. I think it was I don't know if it was a semi or just a regular truck pickup. The wheel come off, come flying through the ditch, jumped through the ditch, run through the ditch, and his garden was close to the highway and hit him and killed him. He was like 80-some-odd years old and hit him and killed him. That really happened some years ago. It was close to here, North Alabama. So yeah, even after it rolled a while, I've heard stories of truck tires coming apart, the wheels coming apart, because, you know, they're two-piece rims, most of them, and hit a truck and just trimmed the side of the truck, the outer panel of the quarter panel, the outer metal. You know, it's two pieces of metal. If you ever looked at a cross section of a truck bed, and just like someone took 10 shears, he said, and just trimmed the sheet metal off the outside layer, just cut just as smooth as could be. After it did that, it glanced and went across the road into the ditch and cut 3 or 4 strands of a barbed wire fence before it finally stopped. Just cut them just as smooth as just like somebody cut them with snips. So, moving wheels, truck tires, car tires, even off a house trailer. I almost got hit by one. It's going up Brindley Mountain and Georgia Mountain, and a house trailer was about 3 or 4 cars in front of me, and I saw the wheel come off and traffic coming this way, and it was coming literally right down the middle of the road. It hit a car. Thought it was going to hit me, but it hit a car and bounced, glanced off the car, and just kept going down the middle of the highway. Fortunately, I got by it. So, yeah, be careful when you're behind those house trailers. Very dangerous. Okay. All right. Then what about spheres? Solid is 2/5 mr squared. Hollow is 2/3 mr squared. Okay. Again, notice how we measure the radius from the center, all right, of rotation. All right. And again, these are on page 286. Okay, so you've got 1, 2, 3, 4. You've got 9 different equations. Okay. So if you wanted to know the moment of inertia of a basketball, a soccer ball, okay. If you want to know the moment of inertia of a bowling ball, okay. Now you know why we don't roll basketballs down and hit the. It's not going to have very much moment of inertia, is it? Not going to have a lot of inertia. But you throw a bowling ball, yeah. Okay. All right. Of course, it's not just its mass when you're bowling. It's not just the mass. It's the energy you give the ball. Okay. Mm-hmm. Okay. Now, what about something called the parallel axis theorem. I thought I'd go ahead and show you this. If you've ever watched baseball games, which I know you have, most everybody has, you ever notice how sometimes they'll choke up on the bat? Okay? Especially if they're going to bunt. You ever noticed how they bunt? They don't want to hit the end of the bat with the ball. They do what? They choke down on the bat and they try to hit it right in the center, don't they? Okay? Well, why? Well, if you've got it gripped at both places, you ever notice where they grip it? They usually grip it, what, right in here? It's close to the center of mass, isn't it? You don't want to give it very much energy, do you? You don't want to give the ball very much energy. So they'll grab that bat and they'll choke down on it and they'll try to hit it right somewhere in the middle. Okay? And basically what you're doing is you're decreasing the inertia, the moment of inertia of the bat. However, if you want to hit a home run, you ever watch the big swingers? They don't grip it up high. They try to grip it down as close to that bottom of that bat as they can. Okay? All right? And of course, why? Well, because you have a much greater inertia. If you grip it at the bottom, you get a lot more torque. That gets into torque, too. You get a lot more torque. Same thing with the golf club. You ever played golf? If you hit a drive, you grip it on the grip, don't you? But if you're wanting to keep it low, not get it up high, you grip down on the club and you punch it, don't you? What are you doing? You're changing your inertia. You're changing your point of rotation. Okay? You grip down on it and you punch it out. Okay? All right. You're not going to get as much power. Even if you swing a little too hard, it's not going to go quite as far. You grip down on it. Same thing with the bat. If you don't want to hit it very far, if you just want to hit it over, you might grip up on the bat a little bit. Hit it over first, hit it over third, and again, that's pulling the bat too. There's a lot of skill in that, okay, which I never seem to have been able to. And what about the Earth? What about something like a planet? I want to find a moment of inertia of the Earth. Okay. Notice it's the integration of its what? Volume, isn't it? So the density, so we integrate the radius squared times the density with respect to the volume, don't we? We integrate it with respect to the object's volume. So we know its radius, we know its density, we can integrate its volume and find its moment of inertia. So the Earth compared to Jupiter, which one's going to have the greater moment of inertia? Even though the density of Jupiter is less than the radius and the volume, yeah, it's really going to make up for it, isn't it? I mean, yeah, Jupiter has a density about a third of the Earth, probably half, third, somewhere in there. But like you said, its radius and volume makes up for it, big time. So if you want to get hit by a planet, another planet get hit by a planet, you don't want to get hit by Jupiter. No, we don't want to hit by anything. Not even the moon. Not even an asteroid. But still, of course, you got to take into consideration energy too. But do stars collide? Sure they do. Do have planets ever collided? I'm sure they have somewhere, because there's other planets out there. It's possible. Yeah. Mm-hmm. Yeah. 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 That's one of the theories, how the moon was formed. Yeah, absolutely. Okay. Okay. All right. All right. And I think that's it. Yeah, that's it. Yeah. I probably won't quiz you. I'm not going to quiz you on the last two. I just wanted to show you that, the parallel axis theorem. Okay. We got a little bit of time.